Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's program is introducing the spectroheliograph, how using a spectroheliograph allows us to image the sun in narrow wavelengths. And here to tell us all about it is Gordon Hansen, a fellow Ford Club member. Gordon, welcome back to the show. It's been such a long time.
Yeah, glad to be here. Thank you very much, Don, for inviting me.
Well, you're welcome. So let's start out with, how did you become interested in imaging using this instrument?
Well, I've been an astrophotographer for about 10 years, and it's mostly deep sky. But last September in Sky and Telescope, there was an article about spectroheliographs, and I read it, and the whole concept of it caught my imagination, and I decided that I needed to build one. So off went my quest.
Okay, so exactly what is a spectroheliograph?
Well, the clue comes from the name itself. So if we do a little breaking down of the word, spectro, we're going to be talking about the spectrum.
Okay.
And helio is sun, so we're looking at the spectrum of the sun. And graph is an instrument that does imaging or pictures, in contrast to a telescope, which is for visual use. So,
okay.
So that's kind of the hint of what this is. It's a thing to look at the spectrum of the sun and make pictures.
All right.
That's the short story.
Okay. Well, what's the most common way to view or image the sun?
Well, the most typical way, especially as people are getting beginning, and what we've done for looking at eclipses, whatever,
Sure.
is a white light filter. It's a filter that drops out 99.99% of the sun, so it's safe to look at. And with that, as the image shows on the screen, we can see sunspots and some other surface details. And those things are relatively inexpensive. And by the way, let me talk right up front here. You should never, ever point a telescope or a pair of binoculars at the sun and look through it unless you have the right kind of filters on the end. You can do some really serious damage to your eyes. And you may not know it right away. It may take 24 hours for the damage to show up, but by that point you're in some deep trouble.
It's too late because our retinas don't have pain sensors.
Right.
Exactly. So a good warning and good safety feature for everyone to follow. So we were just talking about filter, and any other safety tips?
Well, that's the big one. You certainly don't want to be looking at it, and you also got to be a little bit careful when you're imaging the sun. Any plastic components to get on the wrong end of the telescope, you can put holes in things pretty quickly.
Well, that's why when we put filters on, they're in front.
That's right.
I remember way back in the day they used to offer solar filter eyepieces, but you've got all that energy coming through the scope.
That's right. That's the wrong place to put it. So
exactly.
Right.
Exactly. So I guess we've got a little bit of solar physics to discuss.
Yeah, so when we bring up the first image here, showing what the sun looks like, good. So what we're primarily going to be looking at is the photosphere, and that's where the sunspots are. And you can see it's about somewhere between 4,000 and 6,500 degrees Kelvin. And that's the visible surface of the sun. And the important thing here is that that part of the sun, is the atmosphere, so to speak, is mostly hydrogen. I think it's 73%. A good chunk of helium, and a remaining 2% of other elements that were in the sun when it formed.
Like oxygen and iron.
Oxygen and calcium.
Calcium.
And that type of thing. But hydrogen and helium are the predominant ones. So if we go on to the next slide, we can look a little bit now what the solar spectrum looks like. And you notice that this curve is not smooth. There are notches in it. And if you look right in the middle of the red zone, there's a pretty dominant red. That's called the hydrogen alpha notch. So what's happening as the light is passing through the sun's atmosphere, the hydrogen is hot and ionized. It grabs and absorbs some of the photons at that specific wavelength called hydrogen alpha and absorbs it. And then similarly, if we come down a little bit further, right about where the blue and the green come together, you'll see another notch. That's called hydrogen beta.
Okay.
Okay, And then way down in the purple region, there's two dips, and those are two calcium lines. And we'll talk about those in a bit and show some images. But another thing to be looking at here is, because we're going to be talking about absorption lines, you can see that those notches, I don't know, what, they're taking off about 10% maybe of the light. It's certainly not taking all the light away. But when we see some of the images in a bit, those lines are going to look very dark.
Okay,
And you think there's nothing there.
the Fraunhofer lines.
That's right. That's exactly what they are. And there's still lots of information in there. And at very bottom of that peak is where we're going to try and do our work. And is actually what's happening on the sun's surface from in this case hydrogen is now picked up in what we form the images from.
Oh, okay. All right. So it works in that method of picking up from those valleys, if you will?
Yes, that's what we're going to concentrate on.
Okay.
So let's look at the unit I built. Should be the next image. Okay, and this is kind of a breakdown of what the unit is. It's attached to a telescope. You can see the arrow with the telescope on it, and we image the sun onto that disc there that says slit, and that slit is 10 microns wide. So it's a tiny slit, human hairish type thing.
Okay.
And it's wide enough that at the focal length of the telescope we can get the full width of the sun. So that focused light hits the slit, and then obviously some of it, that slit passes through, and now the sun, it got focused, and now it's diverging.
Now you can see that in the pictures
Right.
going towards the collimating lens.
Right, so we hit the collimating lens, which then makes the light parallel, and then it reflects off of a diffraction grating. And the diffraction grating works very similarly to a prism.
Okay.
A prism, you take the light and it breaks it up into its various colors. And the diffraction grating does exactly the same thing, and it breaks the light up into its different colors. Let's go to the next slide again quick. This is another pictorial showing what's happening. So we can see on the left there, by the way, this is all in French. This came from the Solex site, and so I didn't, if you know French, you probably know more than I do at this point. but that light is focused on the slit, then diverges through the collimating lens onto the diffraction grating, and it gets reflected. And you'll see after the reflection that we now have a rainbow occurring.
Yes.
And that rainbow then hits an objective lens, which now focuses it onto the camera that's attached. And you'll see that the red light winds up in one spot, green is at a slightly different position, and the blue purples are at the other end. So if we kind of go back to that first image, you can see the colors there.
Oh, yes.
Okay, and this is adjusted, and you can see that the diffraction grating can be rotated. And by rotating the diffraction grating, we can then choose what part of the spectrum of the sun we want to image.
And I can see on the spectrum there at the bottom, you can see those black Fraunhofer lines.
Yes, those are the lines, and what we're going to do is center those onto the camera.
Now let me ask you, did you purchase this or did you make this?
Okay, mine is called a Solex, and it if you do a search online for Solex 2, Christian Buell is the gentleman's name in France that worked out this rig. And I downloaded, he provides all the files to 3D print the body, and then also some links to other places where you buy the objective lenses and the diffraction grating in the slit.
So this is a DIY
right. This is
unit.
Do-it-yourself unit. And that, I figured, oh, this is going to be relatively inexpensive. But, it works. I'm pleased with the way it's happened. So,
okay.
And then I also had to buy, a relatively inexpensive planetary camera to attach to this thing. So,
okay.
So, if we go to the next slide, I think we can show. There we go. There's the rig assembled onto my rig. So there's a 70 millimeter diameter, 400 millimeter length telescope, inexpensive, an achromat.
Okay, a refractor.
Refractor.
Okay.
And by the way, you probably don't want to be putting your real expensive Petzl designed telescope up here and then pointing it at the sun and hoping that nothing goes wrong.
Exactly.
So this was the easy way, the cheaper way to get going. But you see, I've already had to modify it. Focus becomes a little bit of an issue, and I 3D printed a whole new back end to the telescope so I could attach a focuser that I could remotely focus. The front also has a 3D printed thing with a neutral gray filter out front, because we still got to control how much light power is coming through this thing.
Sure.
And so, but then you can see the rest of it just like in the picture. It's
Okay. Yeah, that's
so
pretty good looking rig there.
yeah. So the point there is that we put it on the sun, and we only get a small portion of. Well, let's see what the next slide here is. Okay, all right, a little history here.
Okay.
This technique is not new.
Yeah.
It's new to amateurs, whatever.
Sure.
But this was invented back in the 1890s.
Really?
Right. And so, and as a matter of fact, the Etalon technology, which is used for, more typically used for doing solar observing, both technologies were invented right about the same time, late 1890s into the early 1900s. So you could, I love the one on the right. It's about the size of a compact car. And,
That's quite a contraption for sure.
And we're going to see in a little bit some of the magic of computer software, but they didn't have that then. So what's happening here is that as the telescope is slewed past the sun, how do we get the image? Well,
Exactly.
what they did there, you can see to the right and the picture on the left, there's a film holder. And the film holder is set up so that as the telescope is slewing, it's sliding the photographic plate across. And so it's only getting that slim image at a time onto the photographic plate. And the next will show some of those early pictures.
Okay, yeah, well, that'll actually be coming up here in just a few minutes. We're going to take a quick break. If you have any questions, please send us an email. As always, the address is down at the bottom of your screen. And we'll be back with more of this conversation after Term of the Month with Stephen.
Thanks, Don. The term of the month is dead galaxies. Large dead galaxies exist in the modern universe. They are dead in the sense that they aren't producing many new stars. Sometimes they are called red undead, since the remaining stars have evolved to older red stars. But many large dead galaxies have been found in the early universe. This is one of the surprises discovered using the James Webb Telescope. This artist's impression of the galaxy Crystal O2 has a huge plume of cold gas blowing out in two directions, nearly the length of the galaxy. This galaxy looked like this 1.1 billion years after the Big Bang. It's a cluster of star-forming clumps in the final stages of collision, causing bursts of star formation. This includes large stars that soon explode as supernovae that then push away the gas needed to form stars. Crystal O2 is forming stars at a rate of around 260 solar masses per year, roughly 3 times faster than expected for a galaxy of similar mass at the same epoch. However, the outflow is removing gas at about 520 solar masses per year, twice the star formation rate. If that continues, and if fresh cold gas is not drawn in from the galaxy's surroundings, Crystal O2 could exhaust or eject its molecular gas reservoir on a timescale of tens of millions of years. No evidence of an active supermassive black hole has been found to power the wind, though earlier activity cannot be ruled out. It is estimated that nearly half of massive galaxies at this epoch are undergoing mergers. This suggests that it's a widespread cosmic phenomenon. Crystal O2 offers a natural solution to the mystery of why these massive galaxies live fast and die young. This study used data from the James Webb Space Telescope and the ALMA Observatory. And that's term of the month, dead galaxies. Back to you, Don.
Thanks, Stephen. We're back with our guest, Gordon Hansen, discussing the spectroheliograph. Now, Gordon, how do you form an image?
Okay, this is where it gets the fun part.
Okay.
And where it's really interesting. As we've been talking, we want to get that absorption line. So we've got the camera telescope focused on the line and the SHD adjusted so the line is in the center. And so what we do is we pass the sun so it's just off the slit. So the sun isn't showing at all. Okay, and then we start the video recording and we slew the telescope across the face of the sun. And what's going to happen is the sun will hit it, and you'll see a little piece, and then it gets wider and wider and wider. It gets to the width of the sun, then shrinks back down on the other side, and then we stop. And this next video kind of gives you a simulation of it. That white line represents what's happening as we slew the cross. We're only getting what's under that line is what's showing up on each frame of the video.
Okay.
And it essentially in the real world is 1 pixel high slice of the sun. So to do the sun, it takes 2,000, 2,500 lines depending on what speed you're going. And so the next image is an actual shot after processing when we and you'll see here's the software starting on the left side. You can see the original. There's the line, and now we're scanning the telescope. And the left side. Keep an eye on the left side. Right about now, you'll see the sun come up, and there's the line. And the computer is now forming the image of the sun as the line goes through, and now we're off the sun. So, and that, depending on the scan rate, that's what you do each time.
So that's your video that
Right. That was done at 32 times the normal sidereal rate. So it takes about, from the time the sun gets started to the end is just under 8 seconds. So it goes pretty fast.
Oh, okay.
Yeah,
so you don't have a problem with the solar rotation messing it up?
That's right. We're only doing 7 or 8 seconds here. Matter of fact, one of the problems you get is, especially if the sun is relatively low, you get the atmosphere boiling and you get all kinds of distortions. And so there is some tricks you got to learn, and going fast helps to mitigate some of those problems.
Oh, okay.
Okay. So maybe we can look at what we get out of this. And
so like why observe using this method?
Yeah, I guess the first thing we would say is that in a typical, what's more traditional solar telescopes that use filters, primarily a technology called edalons.
Okay.
We won't have to get into that. They are very specialized. You buy an edalon telescope for hydrogen alpha, and that's the only thing it can do. It's on that wavelength of light.
And that's the typical solar telescope that we bring to star parties.
That's right. And they started out a while ago with the Coronado PSTs, which were were an inexpensive one, but the edalon in that only did hydrogen alpha. And there've been others out there that are tuned for calcium lines that we talked a little bit earlier. Okay. The nice thing about the SHG, I can rotate that diffraction grating, and I can go to any absorption line that I want to. So we're going to look at some images coming up, but they were all done on the same day, probably within an hour of each other, on the same piece of equipment. So the nice thing with the SHG, I get everything in one package, and you can spend lots of money, or you can go the way I did and build things. Okay. So let's see if we can go through the first image here. Okay, we jumped. This is the calcium line. So we're going to start on the UV side. So this is a shot taken through calcium, and if you see the wider areas, there's sunspots in there. That's typical what's going on. And the white areas here are, I'm going to probably mess up the pronunciation, plage.
Okay.
And they're supergranules, and the color is representing how strong the magnetic field is at that point.
Oh, okay.
So the bright areas are really strong magnetic fields, and the gray are areas where it's less. So around sunspots, that's where magnetic lines are popping through the surface. That's why we tend to see those bright areas there.
Okay.
Let's go on to the next one. Okay, this is the solar continuum. So one of the other things we can image on the line, right? But the line is relatively thin, and we get enough in the image that we can actually go 15 or 20 pixels away from the center of the line, and we now get to the base surface of the sun. So this is essentially the picture you'd get from the white light filters. So I'm getting this at exactly the same time as I did the hydrogen alpha. So it comes along for the ride. Okay, let's see the next one here. Okay, whoop. That's all right. We'll just keep going here. Now we're into some pretty pictures here. So this was hydrogen alpha, and the image on the left is a monochrome as the camera saw it. But that's kind of boring. So we want to make things pretty, so we add a little bit of color to it, and so they're the same image colorized.
Okay, so yeah, getting the contrast.
This is beauty is in the eye of the beholder.
The artistic fun.
That's right.
If you will.
All right, so let's get to the next one. Okay, this is again hydrogen alpha, but this time we inverted the sun body, so the black became white and the white became black, right? Okay. And if you study it, to me it gets more of a 3D effect than a normal one does. And again, a colorized version, and I kind of made it a yellow color just to differentiate it from the colors I use for the. Okay, let's get to the next image. And there's hydrogen beta, which we haven't talked about much. Same as the hydrogen alpha, but we see more of the granules on the sun's surface. And again, I colored this one in a teal color because that hydrogen beta is at the red-green boundary in the spectrum. So.
In the couple minutes we have left, Gordon, how can our viewers learn more about this technology?
Well, I learned a lot online, and there's several people out there that you can go look up. Christian Buell, and he's at a solexastrosurf.com, and I think we're going to have this listed out someplace.
It'll be on the screen as well, yes.
He's the one who put the 3D printed stuff out, and he got lots of information on theory behind it, and so that's a great place to start. He's got a piece of software that you can download that's free that does the processing. There's a Cedric Campeau. He's got one called JSolex, which is a wonderful piece of software. And again, this is all free. There's a Douglas Smith, and he's got a piece of software called SHG Main that does some things in a slightly different way. And then finally, there's if you're looking to buy a thing, there's a mlastro.com. They sell a version of this that you can. So instead of building, you can just go buy your own.
Well, that sounds interesting. Gordon, I want to thank you for taking time out of your day to come in and tell myself and our viewers all about the spectroheliograph. Please visit our website for the club. The address is down there at the bottom of your screen. And coming up next is What's Up in the Night Sky with Stephen.
Thanks, Don. What's up in the night sky for July 2026? The sun goes from Gemini to Cancer this month, with Mercury and Jupiter nearby. July starts with a third quarter moon on the 7th, new moon on the 14th, first quarter moon on the 21st, and a full moon on the 29th. Then we have Uranus, Mars, Saturn, Neptune, and Pluto in the morning, just about sunrise. So Saturn is in Pisces and rises about 4 hours after sunset to 3 hours after sunset over the month. Uranus is in Taurus and rises about 3.5 hours before sunrise to 5.5 hours before sunrise. Mars is in Taurus also and rises the same, 3.5 to 3.5 all month, basically. And then Neptune is in Pisces and rises from 4 hours after sunset to 2 hours after sunset. Pluto is in Capricornus, and it has opposition on the 27th, and so it is up essentially all night. July is my favorite month of the year to see Pluto. 12-inch scope, I think, or better. Then we have Venus and Jupiter in the evening. Venus is in Leo and sets from 2 hours after sunset to 3 hours after sunset over the month. Jupiter is in Cancer and sets about an hour after sunset to rising at about sunrise at the end of the month. And that's because it has superior conjunction, that is, it goes behind the sun, on July 29th. And that's what's up in the night sky for July 2026. Remember, we don't charge money for this show, but we may tax your brain.